Hello everyone. Hi folks. Thank you for being there. I know it's Sunday early in the morning and we have a lot of fun stuff to do and to say and to explain about WebAssembly and what WebAssembly is and how to use it in your day-to-day development, I guess, I hope. So, let's gonna talk about what is WASM and how we can use it and what it is exactly. Is there anybody here that already tried to make some tests with WASM? Yeah, we've got the pure WASM evangelist just here. Okay, fine. So why talking about WebAssembly today? Because it's a buzzy, trendy things for something like 2 years, even if it started earlier that. Because it's really powerful. You can use it already in production, so it's know that you have to get some interest in it. And because we need to extract the domain logic from the browser by itself and run it in dedicated threads and not inside your browser and inside JavaScript, because JavaScript is sometimes not powerful enough to do what we want to do in our web apps. So let's back in history. 2001, we've got prototype, Scriptaculous, MooTools. I'm old, I know. But you too, if you know that technologies. 2005, this is jQuery, and this is the beginning of a new era of application and what to do in our web browsers. Then comes the single-page application, the first bootstrapping of it with Backbone. Then in 2012, Angular. Then the Virtual DOM, React, Vue.js. Then the progressive web apps. And how is your RAM? No, is it okay for you? No, because mine with 8 gigabytes isn't enough sometimes with just my web browser. So we've got a problem here, and we have to solve it in a new way than we do than before. So there is WebAssembly and the WASM thing for 3 main reasons. The first one is that it's fast. I mean, really, really fast. It's close to native performances right into your browser, which is just awesome. It's secured because it's designed to be run in a secured environment, so it's okay. And it's a new write once run everywhere thing, but maybe this time it could be a really good challenger for this topic, because you can run effectively WASM binaries both in the browser and outside the browser and inside IoT things and so on. So maybe it's a new premise of write once, run everywhere. So WASM. What is WASM exactly? At the beginning, there is emscripten. Emscripten is a try to run some C and C++ code inside your browser. So it's something that transpile C code into JavaScript. It is particularly slow, and we need to optimize this try. It wasn't really relevant at the time. It was just an experiment, but it leads us to something more efficient, more powerful. And the thing is WASM.js. In fact, with the emscripten thing, we identified some subscript of JavaScript that we can optimize directly in your virtual machine. So we made this part of optimized things, and it becomes to be it became WASM.js. So this is the first try to do something that is compiled for a language to JavaScript or to a subset of JavaScript optimized for our virtual machines and so on. Fact is, JavaScript is asynchronous and event-driven. We're all okay with that, I guess, I hope. So the JavaScript thing is complicated because if you want to run another languages in JavaScript, most languages aren't asynchronous. Most of them are synchronous. None of them also are event-driven. So we need to transpile or transpose some concept from one language to another. And this is a big challenge. Another challenge is that when we work in a web browser, we're in a single thread. You have the main thread, which runs the layout, the painting of your browser, the render of your web pages, and JavaScript things. So if you block your main thread with heavy things, heavy tasks in your main thread, you block your entire browser with some issues for your users, like random scrolling things or panic clicking on buttons because nothing responds anymore. So we have to solve this problem too. And we have to prevent some things that are the transposition of classical development for our web developers. I mean, we started to work on web pages, and we started to develop web pages. And progressively, we moved to develop some application inside the browser, which is not the same thing. Because on a web page, you just have to refresh your page. And if you refresh your page, you just drop everything out and start everything from scratch again. This is not valid if you want to develop an application, because you have to take care of your memory leaks, of your pointers sometimes, and how you handle something inside your application. So we are just moving more and more from web page design to an application design. And this is what the progressive web apps era are bringing us on. So we have to adapt our way to develop and to bring some code. In fact, we need concurrency, and we have concurrency right now in our web browsers. We have web workers and service workers. So this is detached threads that are dedicated to run JavaScript things inside your browser. So we can already do some things to improve our performances, but we need more and more performances because we are computing most of things inside the browser. We are doing more and more application inside our browser, and we need to optimize them. So WebAssembly is a new language close to machine code instructions, an assembly language, which allow you to run close to native performance your code in your web browser. So this is WebAssembly code. When I saw that for the first time, I just said, wait, okay, but that's not a language. I cannot develop that way. I'm not an assembly guy, and I do some assembly things when I was in college, but this is a long time ago, so I can't do that, and not in a day-to-day development basics, especially for the web. So, finally, if you want to write your code in something more understandable, you have that syntax, which is more assembly things, but this is not really available to a day-to-day work too. You can write it, but you probably don't want to do that. So you have to compile for the web architecture. You have to use a compiler, probably LLVM, because this is the best thing today, and GCC has to die. And this is a modular compiler, which is dedicated to just compilation toolchain. So if you want to do that, you can use any language that could compile, pass it through LLVM, and get a WebAssembly binary at the end that can run into your browser. Why? Why to do that? Just because we can do it, and it's fun. And more because it can address what JavaScript can't address. It can have a dedicated code base. You can share between various projects. You can share your models. You can share your domain logics between the various projects which are written in a dedicated language and which could be compiled to run in your browser. So your browser is a virtual machine right today, because you have all you need to have to handle any use case and development. We can write progressive web apps. We embed web technologies in many things with Cordova, Electron, or so on. So WASM is just another step close to native application, but in web technologies. So WASM is a compiled language using LLVM, which compile any language through LLVM to WASM. It is loaded in JavaScript, with JavaScript. It is executed in your browser, and it is available on your server right now. So back to the basics. In fact, it's not that easy. I had to explain just a little bit quickly, what is a stack-based VM? When you want to develop a web machine, a virtual machine, sorry, ready to execute your code, you have the choice between stack-based VM and registered-based VM. A register is more close to the way CPUs work and the way random access memory works. It means that you have a register, you have some pointers registered in the register, and it allows you to point to some part of your memory, and it's really fast, really optimized, not really easy to develop. On the other hand, you have a stack-based VM, which are more flexible, which has just like a pile of plates that you put on it and shift over time. It's more flexible, it's lightweight, but it's not as optimized as a register-based VM. But in fact, every virtual machine today are stack-based VM. So why not continuing to using it and using a stack-based VM for the WebAssembly virtual machine? So a stack-based VM is something like that. I have my stack with my pointer. I push a primary instruction, which is just here, just one. I push a second instruction, just two. And I push the third instruction, which is add. And when I push the add instruction, I just empty my stack and push in it the result of the last instruction. So I just empty the stack, push the result, the 3, and so on. And everything works that way. So I have two stacks, the stack for the memory, which is just here, and the stack for the instructions that are just added over the time. So the stack is the main point. If I want to write some kind of code, something like that, I want to write this operation inside my stack-based VM. So I will push 1, then push 2, then push a 3 and a multiplication operation. Then I push a add instruction, then I push 7, and I push a divide instruction. And this is kind of close to the reverse Polish notation. And in fact, I can write it like that: push 1, push 2, push 3, multiple, add, push 7, divide, which is close to assembly code. If you already wrote some assembly thing, it's close to that kind of instruction. So let's develop a logic engine, which is based on the JavaScript engine. For the web browser, we don't implement in the web browsers a new virtual machine. We use the already existent JavaScript engine. Why? Because there are already a lot of available virtual machines like SpiderMonkey, V8, Chakra, and JavaScript Core. And at start, we first wanted to run a JavaScript VM engine and WebAssembly VM engine. And finally, this is too much back and forth between both engines. So we mix them, we merge them together. And this is the same engine that run both JavaScript and your WASM code inside your web browser. It means that you have just one virtual machine inside your web browser responsible to run every languages available on your platform. Because the JavaScript engine is both an interpreter and a compiler. I mean, today, when you run some JavaScript, your code isn't executed right there. It is compiled before to be executed into your browser with a just-in-time virtual machine. So we take those powerful virtual machine to bring much more power in WebAssembly. Because the just-in-time compiler produces code machine instruction, but is limited. It's limited because your JavaScript isn't typed, your JavaScript isn't deterministic, and you have to be deterministic to perform more optimization. So we have to optimize it away. This is the way the WASM engine works. This is quick exchanges between the JavaScript engine and the JavaScript thread and the WebAssembly thread. It prevents from unboxing thing. Unboxing is the fact that in JavaScript, when we use variable, you have to wrap it in a box with some headers, some metadata associated to it to present what type of variable it is and how to use it inside your compiler. And because WASM is strictly typed and statically typed, you don't have to deal with the unboxing thing. So this is already handled directly into your virtual machine. It allows you to do monomorphic calls, which are calls to a function that returns the same type at the end as the type that is passed as argument at the start. So it is, again, powerful enough. And it has a lot of built-in methods to prevent some back and forth inside your browser. So the execution engine is now able to run any logic languages directly on the web because they are compiled. So which one to use? The one you want. But I recommend to use Rust. Why? Because this is a really good operating language, system language, because it is dedicated to WASM today. There is a big part of the Rust community that are working to bindings to WebAssembly and JavaScript dedicated in Rust. So if you want to learn a new language, and if you have to learn a new language to run WASM code inside your browser, take a look to Rust. Why Rust? So because C++, thank you, I have only one brain and I can split my brain to deal with memory on one side and logic business on the other one. There is no data race by design in the WASM thanks to the ownership and the borrow patterns. There are static types like in WebAssembly directly. There is a powerful iterators, an excellent memory management, a fantastic community, an awesome toolchain. So no, Rust is really good. Simple hello world is Rust is something like that. So this is not way far to be understandable. This is really, really simple to use. There are modules by design inside Rust, and as JavaScript developers, we love modules, I guess. So it's really easy to use. And there is static types and iterators. I mean, if you want to pass a function in Rust, you have to declare your arguments and the types of your arguments and the type of your return data. Then you have some kind of iterators like a range, and I could fold the range, make a reducer in it to get a sum, and it returns the sum because the last line is an expression, so the expression is automatically returned. So it's pretty easy, pretty elegant, and pretty smart as a language. And there is this awesome toolchain with Cargo. Cargo is a builder upon the Rust ecosystem and is built by the maintainers and the creators of Bundler, which is the same tool for Ruby and the Ruby gems. So they take care of their experience in the Ruby ecosystem and port them to the Rust ecosystem. And this is a really good tool. It's really easy to build, to compile, to run any code in Rust directly on your local environment. So, long introduction enough, but how to use it in production? Nowadays, we have the Fantastic Four. They all support WebAssembly natively in their latest implementation, except for Internet Explorer, but Internet Explorer must die because Edge is the future. I guess, I don't know. This is an open standard. So there is a proposal, there is a standard pushed by the W3C. So this is something really strong, we can rely on it. So we can run some hello code, hello world code in Rust, but dedicated to WASM. If I want to make a greet function, I have just a public function with each greet. We take a string as argument, and I call the alert method. I pass it to the format macro, which is dedicated to format some strings. And I put just a hey and the variable, and I've got my hello world ready to run in the WASM browser. This code compiled to WASM and can be executed in your browser. Okay? Right. So, what's the execution timeline when you want to run a WASM module inside your browser? First, you have to fetch it. You can't yet use directly a script tag with a type WASM inside your browser. It is blind, but it's not available. So, right now. So, you have to fetch it using a fetch request. Then you've got it, you have to load it, you have to compile it twice, because there is an optimization the first pass, so there is 2 passes. Then you can instantiate it inside your environment, and then you can access the function. So it's something like I fetch my WASM module, then I've got the response, which is a binary, so it's an array buffer. Everybody is comfortable with array buffers in JavaScript? And dealing with binary in JavaScript? Yeah, it's a pain in the ass, so forget it. So it's you get an array buffer, which is an instance. So you've got your instance, you instantiate the WebAssembly virtual machine using this instance. Then you've got access to the module, and inside the module you've got access to the various functions that were exposed. So if I retake my precedent code, I get access in my module to the exports inside the module to the grid function that I can call with the forks. Heh! And it works. Nice, pretty nice. Okay. Problem is, I've got 4 static types inside my WebAssembly virtual machine. I've got 2 integers and 2 floats. And that's all. So that's a little bit small. So I need more than numbers. I need other things. I need some complex things that like strings, which are a big pile of shit, because strings is really, really complicated, and numbers are really, really simple compared to than strings or arrays or so on. But a number could be a memory pointer. So I could use inside my WebAssembly code my numbers are as a pointer to some dedicated space in a dedicated memory range to access some part of the code and execute it directly inside my machine. This is why I've got only 4 types inside my WebAssembly code right now. So it leads me to the linear memory. What is linear memory? Let's say I want to instantiate a new WebAssembly module. I have to initialize memory for this module. So I've got the memory. I initialize it with a dedicated starting block, let's say just 1. I will build a shared memory between my JS thread and my WebAssembly virtual machine. So I create a new binary array with a U8 unit integer, unsigned integer 8 arrays, and I pass to it the linear memory buffer. Then I want to get a pointer to this memory, so I initialize a pointer. And I have this string, hello world. So for each character in this string, I will convert it to a binary format. Then I will pass it through the rest of my detection. So I will convert each character using its binary form to its car code, and I will put it inside my shared memory at the given index. So I will have a shared memory which is composed only with unsigned 8-byte pointers that I can pass to my WebAssembly module. Whew! Let's take some water. So, don't do that at home, kids. Those guys are professionals. We can't use it directly inside our browser in this form. This is not possible. I don't want to deal with shared memory. I don't want to emulate a RAM directly inside my web browser. I have other things to do. So, fortunately, there is some tooling. The first one is the WASM Bingen. It's a project which is maintained by the Rust community, written in Rust. This is why Rust is probably one of the best languages available right now to run WebAssembly code. It's a high-level platform that abstracts any calls that like WebAssembly module instantiation, shared memory, linear memory, and so on, to access this directly inside your JavaScript modules and JavaScript engine. So in my Rust code, I will just instantiate my WASP Bingen primitives, and I've got access to the main domain directly inside my Rust code. This is just global things in my JavaScript, so the document, the window, everything is available directly inside my Rust code, even if I'm not in JavaScript thread. So I've got access to the basic functions global, like the alert function, which take a string. So I redeclare in the Rust code the functions that I want to use directly in my Rust code, but that are JavaScript functions. It also works with my own module, so I can write a JavaScript thing, a JavaScript binding that exposes some custom functions directly inside my JavaScript code and import it inside my Rust code and use it directly inside my Rust code. And I could export some Rust function directly to this JavaScript module, and they will be available directly in my WASM code. So if I want to use this kind of code inside a Rust code, inside my JavaScript, directly in my page, I just have to init my WASM module, and I will simply load the WASM binary, and it will return a promise, and in this promise I've got access to the functions that are exposed. So I can call the greet method. The greet method calls the alert. The alert is the alert that is just here. It's a global one, so it's a JavaScript one, so it will call the JavaScript alert function directly when I call it in the Rust code. And trust me, it works. So with WASM Engine, you've got access to exported JavaScript function directly into Rust, all the JS types, I mean all the types, even strings. You've got access to the web system environment, canvas, a request animation frame, performances, everything is just right here. All the JS system, and even the promise that are bound to the futures in Rust that are kind of the same thing. But compiling directly from Rust isn't really easy right now, so there is another tool which is WASM Pack. And WASM Pack is a tool upon the cargo builder, or the cargo bundler inside the Rust ecosystem, which allows you to pack everything and generate all the package you need. So you don't have to compile by hand. You just have to install the WASM Pack tool and simply run it on your code, and it will generate the JavaScript that you need to import to get access to all the Rust functions, the WASM binary, and even the package JSON file if you want to publish your module with the WASM binary directly on the npm registry. It's also already available. So it's really simple to use, way more simple than doing everything by hand, because WASM stay a low-level language. So let's talk a bit about a state of WASM right now. I made an experiment, and because I'm a little bit involved in ciphers, security, cryptography, and so on, I wanted to work with some kind of blockchain things because it's trendy enough too. So a little reminder, a blockchain is an array of nodes. Each node contains an ID, its parent ID. This is because it's chain, because each block is linked to the previous block using the parent ID. It contains a nonce in the traditional cryptocurrency things, and it contains an array of records, and each record is an object with an ID and a payload which contains whatever you want. Okay, fine for everyone? Okay. If I want to mine that blockchain, I will have a loop. I will first try to generate a nonce, which is just a big int, a long big int. I will generate a new node ID using a checksum. The node ID is just a SHA-2 checksum, and this checksum is made with the node parent ID to get the link, the nonce previously generated, and the whole content of the record, basically. Then I will get access to this new ID, and I will try to solve the math problem to detect if the checksum start with an arbitrary number of zero, an arbitrary number of leading zeros. So if I've got the required number of zeros, the problem is solved. So the block is mined, and I can go through the next block. If it's not the case, I do it again. So I generate a new nonce and trying to find a new nonce that allow us to get an ID that starts with a required number of leading zeros. And I shuffle the records because I increase the entropy in it. This is a JavaScript version of this code trying to mine the blocks. If I want to write it in Rust, I just have to write it like that. I made a loop. I mine the node, and if the node is correctly mined, I break the loop. Because I've implemented the logic not inside the core code by itself, but inside the struct. Because you work with static types, so you have to declare the types of your variables. So I have to make a record type and a node type, and inside my node type, and implemented a function that is allowed to generate, to shuffle the records, and to generate a nonce, to generate the ID, and to try to figure out if the ID starts with the correct number of leading zeros. Okay? Did I lost everyone, or is it understandable enough? Okay, so let's try it. Let's make a try. I wanted to get my cursor first. Please, okay. So I've got 3 blocks. The first one, which is the beginning one, here is the parent ID, here is the current ID, here is the nonce, and here is the records. Each block contains 1,000 of records, which are a bunch of objects containing an ID, an email, a name, a CD. It's a pretty good record, like in database. And there is 1,000 in each block, okay? So I will try to mine some code and mine the nonce with 2 leading zeros for the nonce. If I want to mine it with JavaScript, it will start to shuffle the records, trying to get a nonce and try to get the correct IDs. And when the block is mined, the ID is used as the next block parent ID, and we try to get it, and so on. Here I made 340 rounds in 8 seconds, so it's something like 26 milliseconds per round to get it done. Okay? Let's do it the same with WASM. My problem is I'm lazy enough to implement the real-time render in the browser because it needs some post-message back and forth between my Rust code and my JavaScript code, so fuck off. So it will mine it, but in the background, and the content will be rendered at the end, okay? So nothing will move. I will block the main thread with it because I was lazy enough to implement the web workers too. But if I want to mine it, I reset my state. I start to generate. Maybe my browser will be blocked at some point, and I will get the alert that the script is slowing. Oh, no, not that. So 912 rounds in 10 seconds, so something like 12 milliseconds per round, compared to 26 in JavaScript. So it's fast. It's really, really fast to do exactly the same thing. Well, so back here. Yeah. No. Yeah. What's under the hood? Right now, what is the status of WebAssembly? We can, right now, I am stuck in my... Yeah, I can compile any code through LLVM to a WebAssembly binary. You could do it in Rust, but you could do it in anything that could compile. So it's a C, C++, C#, even Python could be compiled. So you can do it in everything you want. It's fast. We proved it. It's lightweight because binaries are binary, so it's more lightweight and more efficient. And we have linear memory implemented through typed array. This is not really easy to use, and we can't have access to the garbage collector right now in WebAssembly, but we can. We have some kind of workaround thanks to WASM engine to do it. So we can access to JavaScript objects and share objects and functions and codes directly, and APIs directly from JavaScript and WASM. We've got a server-side implementation using the WebAssembly system interface. So we can run WebAssembly directly on the server side. I mean outside of the browser. We've got interface types, which are pretty new and allow us to share some kind of APIs between any kind of codes anywhere in our various implementation. And we have some binding modules for any languages. It means that if I want to use a WASM binary somewhere in my executed code, which could be in Python, in Ruby, even in PHP, or in Node.js, fortunately, you can load, thanks to a kind of server-side binary virtual machine dedicated to WASM. You have some bindings allow you to load WASM modules directly into your Python code, Ruby code, or whatever you want. So you can share already some WASM binary through many projects. What about the security of the WASM? This is one of the main features and the main topic of WASM. It's sandboxed. It runs in a dedicated environment, and your WASM code can go to the hosted environment, to the host, without going through dedicated protected APIs. So it's really protected and really secured. It's deterministic. There is control flow integrity. There is a protected call stack with the linear memory, so it means no buffer overflow enough. No way. And it is led by the environment security policies, which are the security policies in your browser, or the POSIX security policies in your environment. So it's strong. It's really strong. And because it's binary forms that can be observed during the runtime, you can tamper some WASM code and leak some data inside it. This is because it's particularly robust to use when you want to do some cryptography inside your browser, because you can implement a cryptography layer in a WASM module and use it to handle your data and your cryptographic stuff. What's coming soon? The multi-threading, hopefully, based on web workers directly inside your browser. So the WASM model will be able to instantiate a new web worker to run a dedicated piece of WASM code. So you don't have to do it by hand, because today, do it by hand is a bit complex, even if it's possible. There will be a streaming compilation with a third compiler, which will prevent the two compile task when you instantiate a new WASM module. There will be more JS module exchange with the garbage collector and a portability of the runtime dedicated to Internet of Things. So it will be a game changer, even if the IoT things. So the conclusion is just know the web. We have HTML and DOM, which are dedicated to declare interfaces. We have the CSS dedicated to layout and style those interfaces. We have JavaScript, which is more and more dedicated to power your UI thread and just the UI. And you will have the JavaScript for all the WASM for all the background processes and the hard computing logics. I'm Mads. I'm a tech evangelist at Always Data, which is a small PaaS provider. And we are working on the WASM ecosystem, and we're keeping an eye on it because we want to propose it to our customers to host some WASM code directly inside our containers for our users. So it's pretty good technology, really, really interesting, and you have to keep an eye on it too. If you got any questions, I'm here. Hello, so don't hesitate to ask and to chat over, we said a beer, but probably more coffee. Otherwise, thank you very much for all your attention.
Questions? Anybody?
Everybody's dead. I killed something like 60 brains.
Okay, so thanks for talk. I'm not the expert in the WASM environment, but are you using it on production, and what kind of performance issue it resolves?
Yeah, you could have some performance issues in production. In fact, the first implementation of my my blockchain things was just I ran it for the first time, and I wasn't I hadn't implemented the run the counter in it. So I ran it through JavaScript, and I got a long result, and I run it into WASM, and I say, oh, it's fast, wow, good enough. And then I implemented the runs, and I just saw that I have less number of runs in WASM than in JavaScript, and the WASM took twice the time of JavaScript, and I said, wow, that's not the expected result. It's supposed to be really fast compared to JavaScript. In fact, I solved the performance issues by refactoring my Rust code by itself. So you have to stack on performances in your dedicated language that you will compile to WASM, and not to the WASM ecosystem by itself, because this is more dedicated to virtual machines, developers of the virtual machine, to implement some performance optimization. But there is some differences. I've got the demo just here run in a Firefox developer, but I've got better results with Chrome, because the Google Chrome team is always implementing some shortcuts in the virtual machine to get faster rendering and optimization. I don't want to know how they do that, but yeah, you have to check to optimize your performances in your low-level language that will be compiled to Rust, to WebAssembly.
Okay.
And do you provide any fallback implementation of your code for the browser which doesn't support WebAssembly right now?
Sorry?
Do you provide any fallback implementation of your code for
Yeah.
the other browsers?
Yeah, we could easily detect if the WebAssembly is available or not in your browser. So you could fall back to dedicated web workers threads in plain JavaScript. You just have to, under the case that it will be probably not that fast, that the WebAssembly module by itself. So, yes, we could definitely do that, but you have to write your code both, one time in JavaScript and the one into your dedicated language, and probably to handle some UX huge case, edge cases, because it will be slow. So you have to prepare your users to have a slowest experience. You could face some performance issues too if you don't have the WASM binary with the correct type in your HTTP server. If you don't have it with the application/WASM type, it wasn't be detected as a WASM module due to security policies into your browser. So you could face also some performance issues even when loading some WASM binary, because it will be loaded byte to byte by your browsers and instantiated instead of just taking the binary and load the binary. So there is some tricks on some parts. This is not dry enough today, so we have probably to be attentive on the way we use it in production, but it's ready to go in production.
Okay, another question.
Hi. So I don't know if you're using TypeScript, but my question is, do you know if, for example, for Rust, the compiler is able to generate typings as well?
Yeah. In fact, the Rust ecosystem is pretty good, because it is statically typed, so your compiler will warn you at compile time about errors, like in TypeScript. Is there a way, is there a project to probably compile some JavaScript to WebAssembly? Yeah, probably. We will probably see something like that allow you to write some code in TypeScript and compile it to WASM to LLVM. So,
but you showed Rust, which was compiled to WASM, right? And you included it in JavaScript.
yeah,
Right. But like, if your project was in TypeScript and you include WASM, would you get typing like
Yeah.
hints and everything?
yeah, you will get the same thing because
so
because under the hood, TypeScript is just JavaScript with static types at the compilation time. So, but you get access to the rest of your WASM module. Yeah, if I understand correctly the question.
we can talk after.
Yeah. Okay. No problem.